Hello, my name is Gabi Pinilla, and today I'll be talking about why we love music, specifically about how sound waves and their harmonic frequencies influence human emotional responses to music. First, let's assume a life expectancy of 80 years. On average, a person will spend around 13 of those years listening to music. Think about that. Nearly a fifth of our lives is devoted to something that, at first glance, could just be called organized noise. Well, music is clearly more than that. However, that creates an essential question. Why? Why do we love music? Why do we give so much of our time and energy to something that doesn't seem to offer any obvious evolutionary benefits? Well, to even begin answering that question, we need to step back and ask, what exactly is music? Essentially, music is built from three core elements. There's melody, harmony, and rhythm. And while it's possible for a song to be missing one or even two of these elements, it must always include at least one of these. However, this is not really helpful. So that's really where my curiosity began. I've always been surrounded by music, whether I'm listening to it or performing it as a musician myself. And the more I play, the more I wonder, why do we love music so much? But when I try looking for answers, I couldn't find anything that felt complete. That's when I decided to start researching it myself. And I realized something. This isn't just about one subject. It's about the intersection of music theory, psychology, and physics. And the best part, it all connects back to science, which I've always loved, especially math and physics. Well, at the end of the day, music is made of sound waves. So let's take a look at the science behind sound. Sound waves are vibrations moving through a medium, usually air. These vibrations travel as waves, and our brains interpret them as music. So, before diving any deeper, let's first get familiar with what a sound wave actually is. Sound waves have four main components. We have amplitude, frequency, wavelength, and phase. So first, let's take a look at how a wave actually looks like. Here are the different parts, but today we're only going to focus on four. So let's break it down. First, we have amplitude, which is the energy of the wave. It's what we hear as loudness. Then we have frequency, which is how fast wave vibrates, which is what we hear as pitch. Wavelength is the distance between two crests. So lower frequencies have longer wavelengths and vice versa. And phase, it's where the wave is in its cycle at a specific given time. And here's the where the math comes into place. Unlike random sounds we hear in nature, musical instruments produce harmonic waves. And here you can see a picture representing two different sounds. First, we have noise, which clearly lacks pattern, and then we have tone, which has a clear pattern. So this idea of harmonic structures may explain why music feel so pleasant. So let's break it down. Harmonic waves are structured vibrations built from a fundamental frequency and its harmonic components. Harmonics are whole number multiples of the fundamental frequency. All these waves layer together and create a rich and texture sound. So, when we listen to a note, what we're really hearing isn't just one wave, it's a whole mix of harmonics stacked together. To study these complex sounds, we need a mathematical tool. And This is what we call Fourier analysis. But what is it? Well, Fourier analysis is the concept of breaking down any sound into its sound waves, which is its simplest building blocks. This idea comes in two main forms. We have Fourier series and the Fourier transform. So first, the Fourier series works for periodic signals only. So, for example, a perfectly repeating note, anything that repeats over time and doesn't change. So, this is represented as just the sum of harmonics. Then we have the Fourier transform, which works for non-periodic sounds, such as speech and music, basically anything that changes over time. So instead of looking at it as just a repeating sum, it converts a sound into its frequency domain, showing the exact frequencies present and how strong they are. So first, let's understand this idea of domains. There's two different types of domains. We have time domain and frequency domain. Time domain is what we normally see. It's just a wave oscillating over time. However, we also have the frequency domain, which is not that common, but it's extremely important because it shows all the harmonic content of a sound. So let's break down mathematically what's going on here. First, let's consider a basic sine function. For periodic signals, the Fourier series expresses the signal as a sum of sine functions. And though this equation may seem a little complex, which it is, we can just see it as just any periodic signal. It tells us that any periodic signal can be constructed by adding together multiple harmonic components, where A naught is the average value of the signal over one period. This is also known as the DC offset. We have A sub n and B sub n, which are the amplitude coefficients of the cosine and sine waves, and they determine the strength of each harmonic. N omega naught is the frequency of the nth harmonic, which is also known as the angular frequency. Each term is the summation, and the summation corresponds to a harmonic of the base frequency. For example, the first harmonic corresponds to the fundamental frequency, while the second harmonic vibrates at twice the frequency, and so on. Now, let's see how these components differ from the Fourier transform, which as I mentioned, works for non-periodic signals. So here is the equation for Fourier transform. F of j omega represents the Fourier transform of the time domain signal f of t. F of t is the regional signal in the time domain. So a sound wave or vibration represented as a function of time. E to the negative j omega t is a complex exponential function that represents a combination of sine and cosine waves. So here, it's a graph of how that would look like. So you can see instead of having two axes, we have three, which are the imaginary axis, the real axis, and the time axis. Omega is the angular frequency measured in radians per second. dt just indicates that the integral is being calculated over time. And finally, j is just the imaginary unit, where j squared equals -1. This imaginary part is essential for capturing both amplitude and phase in the frequency domain. This concept becomes crucial in music because the unique mix and strength of harmonics in a sound is what gives its timbre, which is the color and character of a sound. Timbre is the reason why two instruments can play the exact same note but sound completely different. Let's take a look at this example. Here we can see the same note on a guitar and a piano, both playing a G4. They both share the same fundamental frequency, but their harmonic structures are completely different. The guitar emphasizes certain overtones more, while the piano balances them differently. And that's how we can instantly recognize each instrument without even seeing it. Our auditory system is naturally drawn to order, which is why we find harmonics so pleasing, and while random noise often feels unsettling. And this ability to simplify patterns, it's also why the brain groups notes an octave apart as the same. So now let's take a look at octaves as a natural compression system. So first, for example, let's take an A note at 220 hertz, 440 hertz, and 880 hertz. These are all completely different frequencies, but their harmonics align so well that the brain compresses them into a single category. They're all A notes. And this is just a clear example of how the brain has adapted to optimize and process sound. So, how does this connect to the body? Well, now let's take a look at the auditory system. First, sound enters the outer ear. It moves to the middle ear, where three tiny bones amplify the vibrations. And finally, it reaches the inner ear, specifically the cochlea. So let's take a look at it. Here is the anatomy of the ear. And let's talk about the cochlea. The cochlea is a spiral-shaped organ filled with fluid and hair cells. Each hair cell corresponds to a specific frequency, and this is how we distinguish between different pitches. And here's when it comes the most fascinating part. The cochlea works exactly like a Fourier analyzer. It we can call it like a biological Fourier analyzer. Just like the Fourier transform breaks down sound into frequency components, the cochlea physically separates frequency along its spiral. Here is a picture of a tonotopic mapping of the cochlea. So basically, high frequencies are processed at the base of the cochlea, while low frequencies are analyzed in the apex of the cochlea. So think of it as a roll piano inside your ear. Once the cochlea converts vibrations into signals, they travel to the auditory cortex and then to the limbic system, which is where all of emotions take place. So let's take a look at the limbic system. The two main components, it's amygdala and the hippocampus. They're highly involved when listening to music. So the amygdala shapes emotional reactions such as happiness, sadness, fear, nostalgia. And the hippocampus connects music to memory. And this explains why certain songs take us back to specific moments or remind us of someone. But music also activates the brain's reward system. Listening to music we love triggers dopamine release, which is the pleasure chemical. It's the same chemical that's tied to eating, bonding, and reproduction. And here's the thing, like I mentioned at the beginning, music doesn't seem to have a clear survival advantage, yet our brains treat it as a reward. However, as we've been talking about, this is due to the different mathematical patterns seen in Fourier analysis and our brains natural drawn to order. But this isn't just theory. These concepts shape the real world. So let's take a look of applications of harmonic manipulation. First, we have mixing and mastering. It is important to adjust harmonics in order to polish recordings. Sound synthesis creates entirely new timbres just through harmonic manipulation. And even in music theory, we can use harmonic patterns to influence mood or even aid rehab. And instrument design, shaping resonance to create unique sounds, is fundamental. So, when we step back and it creates a bigger picture and everything is clear. So, first, physics tells us the structure of sounds and essentially what music is made of. Math shows us the ratios, patterns, and even these mathematical tools that makes music organized. In biology, through biology, we can see how the ear processes music and how it really connects to these mathematical patterns that we've talked about. And finally, psychology. It shows the emotional impact and pleasure and essentially why we love it. So, in conclusion, music has become an integral part of the human experience. Its influence goes from dopamine release to even our sense of identity. And though part of its power relies on subjectivity, such as our culture, memories, and personal experience, um, it is clear that science is deeply involved in the why for our love of music. And if we look at the big picture, we can see that it completely relies on an interdisciplinary nature. So it's not just about one thing, it's how it all connects. Thank you so much.